Uh, Welcome back for the last but not least talk of the day. It's a pleasure to introduce Nairita, who will speak about multiscale phenomena in fluid mixing.
Thank you. So do I go ahead and start speaking?
Yes, please.
So I will be talking today about multiscale phenomena in fluid mixing. So what is hydrodynamic mixing? So just to give a brief overview, as we all know, mixing happens when two or more fluids combine to form a homogeneous mixture. Now, there are different length and time scales in the process. For example, mixing of ink in a glass of water occurs in a very different scale than mixing of ocean water with different salinities. Now, in my talk today, I will mainly talk about mixing of systems which are under external forcing, that is, which are advection dominated or turbulent. That is not merely diffusive mixing. And from these characteristics, I will show if we can extract some universal features of hydrodynamic mixing. Now, the mixing process is very important in industries, for example, emulsions or microfluidics, and of course, in natural phenomena, for example, geophysical flows. Now, today I will talk about two types of mixing. In the first part, I will cover mixing between immiscible fluids. So immiscible fluids are those which have a high surface tension between the participating fluids. For example, think of oil and water. Oil has a high surface tension with water. And in the latter part of my talk, I will cover miscible fluids. So miscible fluids, for example, ink and water do not have any surface tension between them. And so they mix in all proportions. So just to give the overview, first I will talk about immiscible mixing and then miscible mixing. And then I will show how I study mixing in oceanic flows using the tools developed in the first two parts. So as I said, in immiscible fluids, I will talk about binary fluid mixing. For example, mixing between oil and water with high surface tension. Now, oil and water mixing occurs very frequently when there is an oil spill in the ocean. And a very good example, this is a picture from the Exxon Valdez oil spill near the Alaskan coast. When we zoom in a small portion of the fluids, we see that there are many oil droplets moving in a background water. So if this is ocean water, the background fluid is turbulent. So we have small droplets of water moving in a background turbulent fluid. So the problem essentially boils down to tracking oil droplets through a background fluid. Now, this is a multi-scale problem. Why? Because there are many scales. So the background fluid, if the fluid is turbulent, which is such in the case of ocean water, the background fluid has many scales, and also it changes the shape of the interface. So the oil and water interface needs to be resolved very well to capture all the interfacial dynamics. And also, if we are considering droplets, these droplets are of finite size. That is, they are not point particles, and the droplet radius is much greater than the interface thickness. So basically, we have to resolve all scales starting from the interface thickness to the droplet size to the scales of the background water. And so this is what I had worked on during my PhD, that is how to efficiently resolve the multi-scale processes in phase separation and mixing. So we used a non-equilibrium statistical mechanics based phenomenon to resolve these multiple scales of oil-water phase separation. And these were the highlights of our research. So as I said, the two fluid mixture, for example, oil-water, has a high surface tension along the interfaces. We use the coupled Kahn-Hilliard-Navier-Stokes equation to simulate such a system. We use the pseudospectral method. And the most important point of our study was that no explicit boundary conditions had to be imposed at the two fluid interface. This is because we used a phase field approach. We used a phase field model, that is the two fluid boundary was described by a set of PDEs for the evolution of a scalar order parameter phi. So I will talk about this in more detail. So the starting point of all my works is the Navier-Stokes equation. And as we know, there is an advection term responsible for all the nonlinearities and a dissipation term. Now, in the first part of my talk, I will talk about Navier-Stokes in 2D, which has some simplifications because the vorticity, which is the curl of the velocity, is a scalar in 2D. Now, so how do we model phase separation in immiscible binary fluids? So our system is the following. You can see this picture on the left. So suppose there are two fluids, A and B. Suppose A is the blue fluid and B is the red fluid, and they are in a homogeneous mixture separated by many interfaces between them. And we essentially captured the dynamics of this interface. That is when this system is allowed to evolve using a set of equations. They phase separate into two distinct phases. So this is how it happens. So all the red fluid come together and coalesce, and in the end we are left with minimal number, that is only one or two interfaces. So how do we model the system mathematically? So we use non-equilibrium statistical mechanics to do that. We describe the entire system in terms of a coarse-grained scalar order parameter field phi. So phi is a field variable because it is defined at every point in space and time. So phi can be the volume fraction, or in some cases the density fraction of a single point in the domain. So VA is the volume fraction of fluid A, and VB is the volume fraction of fluid B, and phi is the overall volume fraction of the mixture. And such definition ensures that we do not have to follow each of fluid A and B separately. Rather, we can consider the two fluids as a whole, as a mixture. Now, we assign a free energy to the system in terms of phi, and the free energy has a bulk potential part, which is important deep inside the fluids A and B, and an interface contribution part through the grad phi squared term. So this is known as the Ginzburg Landau functional. Now for the bulk potential part, we choose a double well potential so that it has minima in the two phases of the fluids. That is fluid A is in one minima and fluid B is in the other minima. And now, how do we find an initial condition for the field phi? To find the initial condition, we minimize this functional with respect to phi. And such minimization procedure gives us a tan hyperbolic function, so that the two asymptotes of the tan hyperbolic are the two fluids. That is, the fluid A is in the negative asymptote and fluid B is in the positive asymptote. And it changes continuously at the interface. So there are no sharp discontinuities. And this is an analytic function. So now that we have an initial condition for phi, how do we find an evolution equation for phi? To do that, we impose the condition that the order parameter phi is conserved. And the two fluids A and B can exchange densities locally. That is, they do not interact over long distances, they only interact over small distances. And the equation for such a conserved order parameter in non-equilibrium statistical mechanics is the Cahn-Hilliard equation, the well-known equation. And so the Cahn-Hilliard equation looks like this, what I have shown in the last line. And so now to model the phase separation of the two fluid mixture, we couple the Cahn-Hilliard to the Navier-Stokes equation to advect each fluid with the background velocity field. And so in the end, we have two coupled equations. So the Navier-Stokes, in which the phase in which the field phi acts back through a surface tension term. So this is like a surface tension term in the Navier-Stokes. And the velocity of the Navier-Stokes is used to advect the field phi. And thus we have a two-way coupled equations. And to talk a little bit about the boundary conditions. So the field phi is greater than 0 in one fluid, in the red fluid, and less than 0 in the blue fluid. And at the interface, phi changes continuously, that is through the tan hyperbolic function. So there are no sharp discontinuities. And this is known as the diffuse boundary method between the two fluids. And this forms the basis of the phase field model that we use. Okay, so some details about the numerical simulations. Our simulation domain is a periodic box of length 2 pi. So we have both simulated this system in 2D as well as in 3D. I will just show some results from 2D in this talk. So we solved the Cahn-Hilliard Navier-Stokes using a pseudo-spectral method, and the time marching is done using an Adams-Bashforth method. And we have codes written both in massively parallel Fortran and also GPU. Now, so the system, the particular system we study is when there is a 50-50 mixture of two different fluids, and the system is under a constant external forcing, and the turbulence is in steady state. So there is continuous rupture and merging of domains. Now we have 4 test cases, and the variable in these 4 cases is the surface tension. The non-dimensional number for the surface tension is the Weber number, which is actually the inverse of surface tension. So the surface tension is the inverse of Weber number. So very high Weber number means So low Weber number is high surface tension and high Weber number is low surface tension. Now, what we see is that in the steady state of turbulence, there is when the surface tension is very high, the two fluids phase separate entirely. That is, there is a black, so this is a grayscale plot. So the two fluids you can see have phase separated entirely into two parts. But as the surface tension decreases or the Weber number increases, the complete phase separation is arrested. This is a phenomenon called coarsening arrest. And this coarsening arrest happens because of a competition between the turbulent drive and the phase separation. So, and the average length of the domain in each case can be calculated. And that's what we did in our paper. So the average length of coarsening arrest follows a scaling law, which is given by Hinz, who gave up the maximum droplet diameter that does not undergo breakup in a starred turbulent scenario. And as I said, this is obtained by balancing the surface tension and the inertia terms in the Navier-Stokes equation. And the Hinz criterion is well established, and we see that our results also follow the Hinz criterion very well over several orders of magnitude actually. This is how we have modeled our system for immiscible fluids, and we find that the results agree with previous well-established results. And thus we can conclude that this Kahn-Hilliard-Navier-Stokes approach to model oil-water phase separation is a valid approach. Okay, so now I will change gears slightly. So far I have been talking about immiscible fluids, which have a high surface tension between the two participating fluids. Now I am going to talk about miscible fluids. That is, fluids which do not have any surface tension between them. For example, water and ink. Now, to do that, we have the following system set up. So we are going to study buoyancy-driven two-fluid homogeneous flows. So what does that mean? So if you see the snapshot in the left, there are two fluids, one blue and one yellow fluid. These are of different densities. That is, the blue fluid is of high density, that is, it is heavier, and the yellow fluid is lighter. Now, there are big blobs of yellow fluid homogeneously dispersed in the blue fluid. So there is no preferred, so the system is homogeneous. And gravity is pointing downwards. And so the two fluids start mixing. And the kinetic energy increases from zero. And at a certain stage, it so happens that the big blobs of yellow fluid get torn up into smaller blobs, and the mixing is maximum, and the turbulent kinetic energy reaches its peak. And this is a snapshot at that stage, at the peak of the turbulent kinetic energy. And this is after when gravity, when the force due to gravity balances the dissipation, basically the turbulent dissipation. And this is a DNS snapshot, 1024 cubed DNS, and it takes about 8 months for the system, for the simulation to proceed from the t equal to 0 state to the t equal to the maximum turbulent kinetic energy state. Now, needless to say, the 8 months is a long time to capture, to study system characteristics. And so the question that we have been asking is there an efficient model for the two fluid mixing? And the aim of the model is the prediction of spatiotemporal evolution of certain correlation functions. For example, the velocity correlation or the velocity density correlation, as I'll show, or the kinetic energy. And the system characteristics, as I mentioned, is that the system is homogeneous, so that the ensemble averaged correlations are translationally invariant, and the driving force is buoyancy. Just a small note that although the full DNS takes 8 months, the model that we developed here at LANL takes only 2 minutes for the same configuration. Okay, so the model that we use is known as a 2-point spectral model, or the local wave number model. So what are the model characteristics? The variables under study, for example, the velocity correlation, are functions of 2 different points in space. So, and that is why this is known as a 2-point model. So it depends on 2 different points in space, for example, like the scale separation. And since Navier-Stokes or hydrodynamic mixing is an inherently multi-scale system, so such a model is ideal to capture the system characteristics, because we need a multi-scale description to capture the evolution of important quantities. And since we have this multi-scale feature inbuilt in our model, it can naturally capture phenomena like initial strong transients. Now, this is just a note that our model is similar in spirit to the very well-developed EDQNM model, which is by far the most important model to capture multi-scale nature of turbulence. But our model is a little bit simpler in the sense that it is physics-based, and we do not consider the time history. So I will talk about this. So in the model, we have the correlation functions. We evolve some correlation functions. For example, the density-weighted velocity-velocity correlation. This is like a density-weighted kinetic energy when the 2 points are the same. And then there is a turbulent mass flux. And then a mixing parameter. This is the correlation of density and specific volume. So the mixing parameter is very much like the free energy in the immiscible formulation. That is, the mixing parameter has a very high value when the fluids are unmixed. And as the mixing proceeds, the mixing parameter becomes minimum. And now, as I said, the DNS takes 8 months, but our model takes only 2 minutes. And how do we achieve such speed up? The reason is there is a reduction of problem dimensions. I will talk about that in a bit. So first we did a coordinate transformation to the center of mass and separation coordinates. And then we take a Fourier transform of each variable. And then we angularly average in the Fourier space, assuming isotropy. And the angular averaging reduces the vector k to a scalar k. And thus we reduce the dimension from a 3D to 1D right there by taking an angular average. And since the system is translationally invariant, we can drop the center of mass coordinate. Now, so I will just show the final equations that we evolve. These look a bit daunting, but they have the same structure. So first, we have the buoyancy production term, and the production term is the same in all equations. The mix parameter does not have any production term because there is no production of mass in the system. And then we have the viscous dissipation term in all equations. Now this buoyancy production and viscous dissipation are exact, that is, they are exactly derived from the Navier-Stokes and are not the model term. The modeling comes for the nonlinear contributions. And we model the nonlinear term as an advection and diffusion in K-space. So all the nonlinear terms in all these equations has the same structure, that is, they have an advection and diffusion of the variables in K-space. And these CR1, CR2, these are certain modeling coefficients which have rigorous theoretical derivations. And the claim is that, such a description, that is an advection and diffusion in K-space, captures all the important, captures the evolution of all the important quantities very well. And that is indeed what we see. So here the blue is the DNS data, which is a very high resolution DNS, that is 1024 cubed pseudospectral DNS. And the orange is our model data. And we see that it captures the initial transients in all cases very well. And the peak, that is the peak at which the turbulent kinetic energy attains the peak. The timing of the peak is also captured very well. The decay part is not captured that well. And we think that this is due to, this is a problem of the model assumptions. But at least the initial transients and the peak are captured very well in all our runs. And we also tested, and the spectra are also very well captured. We can capture the spectra, of course, because our model is a 2-point model. That is, it has multiscale nature. And so we have also used our model for a variety of output number, that is variety of density ratios, and we see that the same set of coefficients give the same level of agreement. And we have also extended the model for a Rayleigh-Taylor mixing case, which is inhomogeneous. That is, this is not translationally invariant anymore. And so there are some changes in the model equations, that is, we have an inhomogeneous direction to account for. And due to the inhomogeneous direction, we have to introduce a turbulent diffusion term, which is one more modeling coefficient. So the system has become a bit more complex. But in this case also, we see very good agreement of the mixing layer with evolution and the evolution of the mix parameter and the kinetic energies in the various planes. These are the agreement in the various planes of the model. And so we can conclude that this spectral model, that is the local wave number model, captures universal features of the underlying system. Okay, so now I will change gears slightly, and I will talk about some geophysical flows. and how we study mixing in geophysical flows. So the two most important components of geophysical flows is the atmosphere and the ocean. And the ocean is by far the most important factor because the ocean has a high specific heat. It has due to the high specific heat of water, and it can retain heat. And so it contributes a lot to global, to climate change. Now, ocean currents control the transport of heat flux around the earth by mixing. That is, this is a very rough sketch of ocean currents around the world. And here the red shows the warm water, and the blue is the cooler water. And of course, due to the ocean currents, the climate near Europe is moderately warm than the other side near the American coast. Now, what are the factors affecting the ocean currents? First, there is the Coriolis force, and then the tides, winds, and waves, shape of coastlines, and density difference. So we have a system in which we simulate, we see the effect of tides on ocean currents. So this is our main work, the effect of tides on ocean mixing. So as we know, ocean tides are generated due to gravitational attraction between celestial bodies, that is Sun, Moon, and Earth. An accurate representation of tides are very important to correctly predict the ocean currents and thus the climate variability. And also tides are important to remove tidal noise from satellite altimetry data. And so the basic equation as we study is the Navier-Stokes with the Coriolis force now playing a very important part. And then we have the tidal force. Now the tidal force is modeled as a gradient of a tidal potential. Now this tidal potential, it has a very nice series expansion in sine and cosine, that is, it has harmonic expansions because of the regular nature of tides. And then we have introduced two drag schemes, that is a quadratic drag scheme and a topographic wave drag scheme. And this is linear in velocity. And this occurs due to scattering from rough topography in the ocean floor. And we study ocean mixing due to these drags and of course the tidal potential of the tides. And so what is the comparison metric? That is, how do we know our implementation of tides is correct? So we have the amplitude and complex root mean square by comparing with observational data. Here A0, here the, O represents the observed data, which is the TPX08 reanalysis data that we use, and M represents the model or our simulation results. And so since tides have an amplitude and a phase, so this is how we take into account the amplitude and phase errors. And we have some very nice results in very high resolution unstructured mesh around the earth. And we see that that the tides that we have implemented are correct within an error bar of about like 5 to 10 centimeters. And so we are working on improving, working on studying how tidal mixing affects the heat flux and ocean currents around the earth. So, and so these are some manuscripts under preparation. And these are some of my journal publications and this presentation. And so with this, I would like to end my talk. And thank you so much for having me here. So if there are any questions.
Yeah, hello.
Hi.
When studying the Cahn-Hilliard system,
Sure.
can you tell me whether the feedback back on the Navier-Stokes equation has any importance whatsoever to the dynamics, or is it essentially negligible?
Oh yeah, so let me share my screen 1 second. Yeah, so the feedback is extremely important because I have not included any plot of spectra, like kinetic energy spectra, but we have the results that it changes the slope of the spectrum very much. That is, if there was no fluid, then the spectrum would be very different, basically.
Thank you. Idris has a question.
Hi, thank you again for a beautiful talk. I have a question concerning, again, follow up on the earlier question by Jean-Luc. You know, I understand the rationale behind the Cahn-Hilliard. However, I mean, you had an ad hoc potential phi. Suppose I take different potential which has minima at -1 + 1. Would this, in a way, affect the dynamics, the results, the statistics, or any of the above?
I see. Okay.
Because it is ad hoc, there is no physics about it. It's like basically just a way to capture the interface in some kind of like one way or another. So it's an ad hoc in some sense.
Right. Yeah. So basically, I mean, of course, yeah, there can be other ways in which we define the same two fluid system, but we do not have such a potential. So you are asking if the dynamics if the steady state results would be different. That we have to check. I presume that that might not be different because the Cahn-Hilliard, so the Cahn-Hilliard equation will not be affected if the initial conditions, the underlying potential is different. So the steady state results might remain the same actually.
Could I interrupt? Can you hear me?
Sure, yeah.
Idris, it's not ad hoc at all. There's very good reasons, very good physics why that phi squared minus 1 squared is good physics. You'd have to read about it, but let me assure you that it is. Yes, this left-hand potential. That isn't just picked out of nowhere. There are very good reasons why it should look like that. You can pick other functions, but this one is well known as the best.
Yeah, I mean, basically, it is good if you want to use a language of statistical mechanics, keeping a phi squared minus 1 whole squared is good near the critical temperature. If you go away from it and you still stay at the level of mean field theory, you might want to replace it by log cosine hyperbolic phi. Okay, it will affect things quantitatively, but qualitatively everything will go through. I mean, she didn't show you spectra, she didn't show you droplet dynamics, which I can tell you offline. But I think
Yeah.
it does get many qualitative things right. And one good thing about it is you don't have to match boundary conditions on a moving boundary problem. Can I ask a question now? Sorry, about the second part of your talk, you said
Yes.
some DNS takes 8 months
Yeah,
and your model takes 2 minutes.
right.
I
yeah.
didn't quite understand what that DNS was. What is the model there?
So this is the Navier-Stokes with 2 fluids. The densities are different in the 2 fluids. So there is an evolution of volume fraction, and a slight compressibility factor is built in. That is, divergence of U is not 0, but it has a slight compressibility. It is divergence of U is log of D. It has a certain function. So basically they're evolving 2 separate equations using a pseudospectral code.
So it really takes 8 months. That's impressive. Okay.
Yeah, this is actually 1024 cubed. Yeah.
All right. Thank you. Thank you very much.
It's a variable density model, is it?
Yeah, yes.
Okay, for Rayleigh, it's a variable density model for Rayleigh-Taylor.
Right.
Yeah, that is
Daniels, yeah.
Daniel's thing. It's very, very demanding, but 8 months is pretty spectacular.
Yeah, I think this was 8 months. This could be for the 2048 cubed actually, but basically to get a very high resolution simulation, order of 8 months, something publishable, it takes order of 8 months.
And the resolution was?
In this case, what we have compared was 1024 cubed. Yeah.
Okay. Thank you.
We have a question from a virtual participant, Gautam. Go ahead.
Hey, thanks. Thanks for a nice talk. I hope you can hear me.
Sure. Yeah.
So I had a question. Can you go back to where you coupled the Navier-Stokes and Cahn-Hilliard?
Yeah, sure. So just 1 minute, I'll just find the full screen mode.
So my point was that maybe in the context of 2 ocean fronts meeting with different salinities, is there, would it be better to couple them by changing the viscosity as a function of phi?
Yeah, that is an interesting question. Actually, there are many, some recent developments where viscosity is a function of phi. Yes, that is a very current topic of research, and that can be done actually. Yes, that is being recently done. Only the viscosity is no longer a constant here, and then we have to adjust the equation slightly, but yeah, essentially it can be done.
Any more questions, comments? Nothing online? Okay, then let's thank our speaker again for a beautiful talk.
Thank you. Thank you so much for having me.